Welcome everybody. This presentation is all about an introduction to flood. Flood is a phenomenon which is classified under the extreme event, and this event occurs due to excessive rainfall or excessive snowfall, and which resulted in a high volume of discharge, which crosses the capacity of water bodies to store water, and which resulted in overflow of dams, reservoirs, canals, river channels, and which is collectively known as the event flood. Now, as I've already discussed here earlier in the earlier slide, that high stage means water level in river. When the river overflows and inundates the adjoining area is a situation described as flood. You can describe it as a situation, or you can describe it as an event. And in any hydraulic structure design, the flood peak and frequency of the peak is a very important parameter which need to be predicted well in advance. Generally, what happens is during a design of a hydraulic structure, the 100-year rainfall having more than 100-year return period and more than 50-year return period is considered as the design discharge. That means the peak discharge observed in the last 50 and last 100 years is taken as the highest level of design with respect to which the hydraulic structure need to be developed. That means this structure must have the capacity to withstand such amount of rainfall, and as usual, this peak discharge need to be predicted for the future, which will help us to understand that whether this structure, whatever we are designing, will withstand the future extreme events, at least for those events which have occurred in the last 100 years. So there are some flood prediction methods, namely the rational method. Okay. This is rational method, QP. This QP is actually the peak discharge. This C is the runoff coefficient. Area, this is the watershed area. And this I is the intensity of rainfall. So it is not rainfall, but it is intensity of rainfall. Now this runoff coefficient is actually the runoff rainfall ratio of that watershed. And regarding I, this I depends upon the time of concentration and the amount of rainfall. It is defined as I equals to K T to the power X divided by T subscript C plus A to the power N. Here K, A, X and M are empirical constant. Okay, Tc is the time of concentration, T is the return period for which you are designing this hydraulic structure, and accordingly you have to design or you have to predict the peak flood. So K is equal to CIA means C is the runoff coefficient, I is the rainfall intensity for that return period for which you are designing the hydraulic structure and for this time of concentration. This P indicates the exceedance probability. This P is the exceedance probability, which is actually the return period in inverse. So if the probability is low, return period is high. If the probability is high, return period is low. So always rainfall intensity is calculated based on a specific return period and time of concentration. Now, as I have already discussed, K, X, A and M are the empirical constant, which depends upon the frequency duration curve. Now, what is frequency duration curve? I will discuss it in another presentation. And one thing you remember, this is C. C is the runoff coefficient, which depend upon the runoff rainfall ratio. So if rainfall is high, runoff is low, C will be low. If runoff is high, rainfall is low, then C will be high. Means C will be larger. So generally, if an watershed is slopy, then C is high. Because for those cases, runoff will be high and rainfall will be low. Whatever rainfall may be, the runoff will be high for the slope, highly sloped watershed regions. Whereas when the slope is not very high, then runoff will not be very high, and so C will be small. So always remember, C generally varies in between 0.1 to 0.9, and this area, that means towards 0.9, it means that this rainfall or runoff is occurring in a watershed which has a very high slope. And for this area, that means towards 0.1, towards the lower value of C, you always remember that rainfall and runoff is both occurring in a watershed where slope is not very high, not very large. So according to the slope of an watershed, this C will change. And yes, so this is the what I will say. So this is the empirical formula. This whatever formula I have just discussed is known as rational equation, and rational equation comes under empirical formula. Empirical formula is those formula which were derived based on the data set of a specific region, and it is not a conceptual formula. It doesn't follow any concept, any governing equation. These formulas are generated from the data set of a specific watershed or specific area or specific region. So generally these type of formulas are valid for those region only from where it was developed. So this empirical formula can give you an idea, but the accuracy of this formula is not very satisfactory. For example, this is your Dickens formula. QP equals to CD. CD is the Dickens coefficient. It values between say 6 to 30. Area A is the watershed area. And the unit is here square kilometer. CD doesn't have any unit. QP is in meter cube per second or cubic. Now, in various books, the unit of area isn't different. It is expressed differently. In some books, it is square meter. In some books, it is square kilometer. So, what I found is, in most of the books, the unit of area is square kilometer. And another point of note is that in most of the book, they have said that just to multiply the Dickens coefficient with the area, and you will find this peak discharge. Here you do not have to satisfy units. So as in most of the book, the calculations are shown in this way. So what we will do is, if you have been given the Dickens coefficient and area, what you will do is you will straight away multiply CD with area to the power 3 by 4, and you will get the result in cubic. Although this area will be in square kilometer and this CD has no units. So yes, the unit in the LHS and RHS will not be same, but as majority of the books shows us the derivation or calculation of Dickens formula in this way, so we'll follow this process of calculating QP with the help of Dickens formula. Now there is another formula known as Ryves Formula. So same thing, area in square kilometer, QP is the peak discharge, CR is the Ryves formula or Ryves coefficient, which value varies in between 6.8 to 10.2. And yes, and as you can see from the values, the CR varies between 6.8 to 10.2, and when this is in the higher side, QP is also higher. So it indicates that for watershed with high slope, CR will be in the higher side, but for low slope watershed, CR will be in the lower side. So this is another one. This is derived from the data of Western Ghats in Maharashtra. This is known as Inglis Formula. So QP 124A. So here only variable is this watershed area, and all these are empirical constant, but it is derived based on these Western Ghats and in Maharashtra. So you can understand that watershed in and around Maharashtra will have greater accuracy compared to the other watershed in the other region of the world. Same thing, Fuller's formula. Now this is, as you can see, this log T is Bulletin period, and the CF is the constant, Fuller's constant, area is the watershed area. And this formula is valid for or derived from US watershed in US. Okay, so another formula, Baird and Mcillwraith, derived in 1951. This is, yes, of course, watershed area. This is our peak discharge. But this formula is derived from the maximum recorded floods throughout the world. That means if all the floods in all around the world is recorded, then and if we take only the maximum flood, extreme flood, then from those extreme floods, this formula was derived. Okay. Now, so we have discussed about various empirical formula by which you can estimate flood. And as you know, in statistics, there are two things. One is synthesis, one is analysis. Another one is synthesis. Now, this analysis involves in collection of data and trying to establish a relationship between an event and its probability, right? That means this analysis section tries to analyze the inherent relationship that exists in between the collected data set. But in case of synthesis, what we do is we try to estimate the probability from its mean and standard deviation. Actually, what we can say is if developing a model is analysis, then interpretation from the model or more prediction of from the model is the synthesis. By analysis, we can identify a relationship. By synthesis, we can conclude, we can decide something. That means if there is a problem, we can decide the solution based on the analysis done upon the data, relevant data, based on that problem. So, in analysis, we try to estimate relationship. In synthesis, we try to conclude the decision from that relationship. So, let us see this calculation of probability density function or of an event, of a series of events, rainfall events or runoff events. Calculation of probability is known as the analysis. But concluding something, deciding something from that analysis, from that probability distribution function is known as synthesis. So here in hydrology, we generally use some specific methods to determine the probability distribution function of rainfall events or runoff events or any hydrologic events. Now, how to do that? Yes, one method is known as Gumbels distribution function. There are normal distribution function, log normal distribution function, Pearson type 3 distribution function, log. So in this way you can see that the event with highest magnitude will have the lowest probability. And if you invert this probability, you get the T, that is return period. So automatically, a highest magnitude rainfall will have the lowest probability. However, it will also have the very large, long duration return period. Right? So this is actually the probability. Yeah, actually the way we have to find the probability of all the events in a data set. And after finding the probabilities of all the data set or all the data points of the data set, we'll have to find the mean and standard deviation of the probability of data in the data set. That means with the help of the probabilities that we found, with the help of p is equal to m by n plus 1, you have to calculate the mean and standard deviation. Now after finding this, what we do is we try to match. Let us discuss about this. As you know that the equation for representing straight line is this: y is equal to mx plus c. Now this is developed based on if you have the data set y and x. So here if y is your rainfall and x is the time in month, then this equation will give the straight line equation or straight line representation of the events, all the rainfall events that we have considered. Now in similar manner, if I say alpha to be the mean, this will remain as x plus beta. That means this beta is your standard deviation, this alpha is your mean. Then this equation, this will be your y. This equation will represent the normal distribution function of the data set. Now if you, similarly, now what you will do is you will put this mean and beta is known from here, right, from the probabilities of data in that data set. Now if x is the probability, x is the time in month, then putting the value of x will yield or will give you the probability of the event which had the position or which had the time scale t in that data series. So if the data series is like this is your time and this is your data. Then if the position is like that, 1, 2, 3, 4, 5, 6, January, February, March, April, May, June, and this is your rainfall, that is the probability of the rainfall in I have one thing, this is not January, February, March, April, May, June. This would be the rank of the event after we sort it in the descending order. The highest event has the best rank and the lowest event has the worst rank. So if we arrange this set like this and put 1 in here, then with the help of this mean and standard deviation, it will give the probability of the event which has the best position with respect to its magnitude. If we give x as second, x as 2, then it will give the probability of the event which has the position 2 or which has the rank 2 in that data set. And in similar manner, we can find the probability of the event which have the rank 3, rank 4, rank 5, rank 6. So this is the way with which we can find the probability of the events arranged from the highest event to the lowest event in a specific data set of rainfall or runoff or anything, any hydrologic events. Now, if the data set follows normal distribution pattern, then the probability found in that state, p is equal to m by n plus 1, and the probability found by using this equation will not have much difference, right? So if I say this probability has probability from the distribution function, and this probability is from the real, the way we have calculated the probability, then this difference will be nearly equals to 0. So if it is nearly equal to 0, that means this data set follows a normal distribution pattern. But if it doesn't follow a normal distribution pattern, then this PD minus P, this PD minus P will not be equals to 0, and it will be much larger number. So it will actually be much larger than 0. So this will indicate that this data doesn't follow a normal distribution pattern, and we have to then test with the log normal distribution function or any other distribution function that I have already shown in the slides previously. Like you can test with Pearson, you can test with Log-Pearson, you can test Gumbel. So any other distribution function you have to test. So the probability derived from that distribution function and the probability, the real probability which was calculated from the event, must not have much difference. If it has less than 20% difference, then that data set follows that type of distribution function. If it has more than 20% data set, then it doesn't follow that type of distribution function. It must follow some other type of distribution function. So in this way, once we note or once we establish that this data set or this set of rainfall events follows this type of distribution function, our analysis step, or the first step of analysis, is completed. And I think with the help of this distribution function, we can find the position of the probability also. If we just interchange PD and X with each other, that means if X is taken here and P is placed here, that means then the equation will be like this: PD minus beta by alpha equals to X. Then we'll get the position of the probability. That means if we know the probability of the event, we can find the position of that event in that data set. But if it doesn't know the probability of the event, then with the help of the position of the event, we can find the probability of that event. But the first step is you must identify what type of distribution function your data set follows. This is valid for any type of events which is time dependent or space dependent. So after finding these two, you see this is I have already discussed P equals to m by n plus 1. Then there is different way you can calculate this P. But mainly P is equal to m by n plus 1 is followed. There are various ways you can find this probability position. Now let us come to synthesis, how to find the magnitude of the event with the help of some probability equations. This is the most popular event. If I know if I want to know the magnitude, if I want to know the magnitude if I want to know the magnitude of an event with having t return period and if I know what is the mean and standard deviation of that event, then you can find this magnitude with the help of this frequency factor, which depends upon the t, or what I will say return period. Uh, then you can find the magnitude of that event. So let us summarize it in a more better way. Suppose I want to know the magnitude of an event, rainfall event, having a return period of t. So if I know the return period, I can know the probability, right? Now, if I put this probability in place of k, and if I know the mean of that set of events and standard deviation of that set of events, I can easily find the magnitude of that event which has the probability p. Right? So this is very easy way of finding the magnitude of an event if I know the mean and standard deviations of that event. So just put the just find the probability with the help of the return period, put it in the place of k, and you will get the magnitude of that event in the return period at that return period. Okay. So these are various mathematical models. Now let us come to the adjustment for urbanization. As you know, if you have an watershed, then some part will be under urbanization or urban type of utilization, and some part will have peri-urban type of utilization, and some part will be rural. Now, in case of urban, the best way to represent urban is the areas which are urban, they are generally impervious, and the areas that those are under rural, they are generally pervious, and peri-urban has a mix of impervious and pervious area. Impervious means after rainfall no water can percolate into the soil, and pervious means water can percolate into the soil. So due to this urbanization, as we know, due to the increase in population, area of urban area is also increasing because people are shifting their rural homes to urban homes, and as a result we have more larger urban area compared to the rural area. So for this increasing urban areas, we have to adjust our equation for estimating peak discharge. So here you can see this is your old rational equation of Q is equal to CIA. After adjusting for urbanization, this has become this, where you can see A is, yes, it is the drainage area or watershed area. Now here this is fraction of imperviousness. This is U. That means how much area is impervious. Now P is the volume of rainfall, TR is the duration of that rainfall. Right? So this is the modified rational equation to include the impact of urbanization. This is the adjustment factor based on the percentage area impervious and percentage area served by the storm sewers. So with the help of this chart, you can find the adjustment factor and multiply it with the discharge that you have estimated from that empirical equations. Now, there is another concept known as probable maximum precipitation. This is nothing but the probability of a precipitation which have the greatest depth, that means the peak rainfall for a large return period. Here you can see PMP is the greatest depth of precipitation for a given duration that is meteorologically possible over a given station of specified area. So this is the PMP means the maximum, what is the probability of the occurrence of maximum precipitation. There are two methods to estimate that. First one is meteorological method, second one is the statistical method. This is meteorological method and statistical method. And this meteorological method is derived from the major historical rainstorms of different duration, and the second statistical method is derived from the frequency analysis of the annual maximum rainfall series for different duration. And as usual, statistical method is very easy to do, as meteorological data is more or less insufficient. Now this is one method of estimating probability maximum precipitation with the help of statistical method. This is known as Hershfield method. Yes, this is mean. As you can see, X, this indicates mean. This indicates standard deviation. This is, as usual, frequency factor. And this can be derived from the chart, or it is calculated based on the K values from all stations. Okay. So this is the way how the frequency factor calculation is done. I have already shown it in the previous slide. Yes, if you know x1, if you know the mean, if you know the deviation, we can find the K. Right, and this is done for all the station nearest to that station, and then some averaging is done, and this frequency factor was derived. Okay. Now this is how to determine the homogeneity of dataset. Look, If there is no change in the data set for a long duration of for the time or a space, then you cannot develop any model on that data set. Your data must be heterogeneous. That means it must have some increasing or decreasing trend with respect to time, space, or any other variables. If your data doesn't have any trend, you cannot develop a model based on that. So whether your data has a trend or not, there are various tests available. Here we are showing this Mann-Kendall rank statistics test, which is used by World Meteorological Organization. And this is the formula. It is self-explanatory. So this is N is the total number of data set, and Ni is the certain number of data, and sigma tau square, that must vary in between plus minus 1.96 at the 5% level of significance. Then it indicates there is no trend. If it has more than 1.96, then it indicates that it has some trend. Now, about this determination of trend in a data set, I will discuss later on.